To your no doubt great relief, this video will be rather short. I'm going to explain what R is and show you the formula that's used to derive R, and then we'll go away. Well, there's one more thing I have to do. That'll be funner though. So R is a number fact about a scatter plot. Don't think of it as a variable, think of it as a, if you were going to describe the strength of a scatter plot, with, you would want a scale of how strong, how weak a correlation is. And R is a number, a single number that basically quantifies that. And here's the incredibly ugly formula. First of all, some facts to know about R. If you have a scatter plot where it's just basically a whole bunch of points in a straight line heading upwards, your value of R will be 1, as in 100%. If your points are in a straight line going down, then R will be -1. It doesn't have to have a slope of anything particular, but if they're in a straight line, -1. That means perfectly predictive. Like if you know the explanatory variable, you would be able to perfectly predict the response variable, and also it's in a negative direction. Doesn't matter how steep. Now, if your points are either in a straight horizontal line or scattered so wildly that there's no positive or negative correlation, you can't use the explanatory variable to help you predict the response variable at all, then the value of R will be 0. And this is the formula that is used to calculate the exact value of R. It's on your formula sheet. Guess what? They will never ask you to use it. It's way too much time spent. I'm going to explain it in brief. So, the sum of, so they take every single point, they take the location of that point and compare to the average, and then divide it by the standard deviation. That might look a little familiar because, hey, it's the formula for a z-score from chapter 2. So let's say a point is 0.3 higher than the average. Or no, let's take an SAT example since I'm going to keep using that. Bob scored 1200. The average score was only 1150, so they're 50 points above average. And the standard deviation was 100, so that person is half above average. Now, compare that to their that's their SAT score. So hey, their SAT score, z-score, is 0.5. They're slightly above average SAT score. But then we take a look at their grades. Their GPA was 2.9, and the average GPA was 3.4, and the standard deviation of GPA was 0.5. Oh my, they are one below, z-score. Their z-score of their grades were -1. Then you multiply those and you get -0.5. And then basically when you add them all together and take the average, you get something magically that comes out between 1 and -1. But the average of a whole bunch of numbers that are about this should come out like that. The point here is that if you're higher than average at one thing and lower than average at the other, then you're contributing some negative correlation to R. So if all of them contribute negative correlation to R, you're going to end up with a negative R, where when you're above average in one thing and below average at the other thing, in other words, here are all the points. For every point that's like here, you're making the correlation more negative, and for every point that's here, you're making the correlation more positive. When you're more of one thing but less of the other, or more of one thing and less of the other, you're making the correlation more negative. So R describes the correlation, and I can estimate for you, or guesstimate the correlation in each of my many examples. So now I'm going to turn this on, I'm going to widen the field so you can see more than just my head and like 5 inches of formula. I'm so good with technology, I know how to use a camera zoom function. They should hire me as the new tech teacher, except then who would teach stats? Okay, so let's run through a whole bunch of these and let me estimate R for you in each case so you'll have some idea what to look for. Yeah, it's the same slide from last time, I'm so boring. Okay, the correlation here is probably 0.98 or something, very strong correlation. Maybe I'm exaggerating a little, maybe like 0.93. Over here, the correlation is negative. It's pretty reliable. I would have to say about negative 0.8, maybe negative maybe a bit more, a bit less, about negative 0.8. There's actually a game you can play online, maybe I'll find it online. My brother-in-law showed it to me, where it's just guess the correlation, and you have to they'll give you a bunch of scatter plots, and the answer is always somewhere between 0 and 1. In this case it's negative, but all of theirs are positive on their website. And you have to guess how strong the correlation is, and if you're within this close to it, then yeah, you got that one right, and if you're too far, you got it wrong. Maybe we'll play it in class. Here's two more examples. Over here I would say R is probably 0.3. And over here R would probably be negative 0.5. Yeah, so reliable correlations are stronger. This would probably have R equals 0.1 or 1.5 or so, because it does look vaguely positive. And over here R would be actually really close to 0. Because it's neither got a general upward pattern nor a general downward pattern. The pattern is pretty equal on both sides. So R over here would be close to 0, I don't know what. Yeah, and that pretty much solves all the examples until we get to our example. Over here I bet you that R, actually I calculated R thanks to the trusty computer and some stat software, and got R equals 0.1 something. So a very weak positive correlation, which is what I told you guys in the previous slide, yay. It was also what I thought before I looked it up. So yeah, slight positive trend, but really not reliable. And I'll show you next KCD slide at some point in class, probably. Yes, 1725. So I forget what its name, Rex Thor the Dog Bearer. Okay, that will do. I've explained R. Oh, no. I explained that, I can move on.